So for IB, we have to do a little bit more discussion with simple harmonic motion, and we want to look at some different graphs. So we've looked at some plots, like the acceleration as a function of displacement, where we get that negative linear curve, or the velocity as a function of the displacement, where we kind of get that hat-shaped curve, or like the dome-shaped curve. Sometimes, though, we're not really interested in how these variables change as a function of displacement. We're actually interested in seeing how these functions change over time. So what we're going to look at, first of all, is we're going to look at how the displacement of the oscillator changes as a function of time. So as it's bouncing back and forth between the two amplitudes, if we look at that as a function of time, we're actually going to get a curve that looks a little bit like this. So this is what we would call a cosine curve. If you haven't done Math 30 yet, it's a little bit this might be a bit more, it might be a bit challenging, but we'll try and keep it as basic as we can. So basically what this is just saying is, okay, we're starting at the amplitude. It's going to start to move towards equilibrium, and then it's going to move to the amplitude on the other side, then back to equilibrium, amplitude, equilibrium, amplitude. So you notice it's bouncing between the two amplitude positions, like one to the right, one to the left. It's continuously going between those points. And this curve has a very repetitive pattern. We're talking all about that repetitive motion. Now, we also know that if we have a position time graph or a displacement time graph, we can also get a velocity time graph. So a velocity time graph, the way we would generally get that from kinematics is we'd start to take the slope of the line of the curve on the dt graph. Well, for this, you can see that the displacement's changing, so the slope is going to continuously change here. Like here, there's no slope, and then we start to get steeper and steeper and steeper and steeper, and then it starts to shallow out and shallow out and shallow out and shallow out. And then at these points here, slope's going to be 0. So like slope is 0 here, slope is 0 here. Now these, in the position time graph, these represent the amplitude positions. We know at the amplitude we want to have 0 velocity. So on our VT graph, here's my amplitude position, here's my other amplitude position, and you'll notice that V is equal to 0 at these points. When I get to the equilibrium, however, because again, this line of x equals 0, that's equilibrium, I'm also traveling at my fastest speed. Now, in this case, because we're moving from right to left, we're going to have the maximum negative velocity. So you're going to kind of see that all of these points where we have a maximum or minimum on this graph, that is going to correspond to cases where we have v equals 0. At the points where we're at equilibrium on our position time graph, that is going to give us those areas where the velocity is at its maximum point, whether it's positive maximum or minimum maximum, or sorry, whether it's positive maximum or negative maximum, that's going to depend on the direction the oscillator is changing. You will notice that this also has a periodic shape. It almost looks similar to this one. You'll see the height off the graph, or the amplitude's a little bit different to reflect that this is a velocity and not a position graph. And it almost looks similar to this, but it almost looks like this graph is slightly shifted. Like, it almost looks like this graph here, like we start at 0, go down and up, but we've just kind of shifted that back a little bit. That's not a coincidence. What we could actually say is that these graphs, this dt graph and this vt graph, they have a phase shift of 90 degrees. We'll talk about what a phase shift is a little bit later. So, and as we mentioned, on the VT graph where V is 0, we're going to have our displacement at the maximum at the amplitude points, and where the velocity is at a maximum, we can get the displacement to be 0. And that's consistent with what we've done so far. Now we could rationalize with the velocity graph to get an acceleration graph, but we also know, that the acceleration is proportional to the negative of the displacement. So if we have a displacement time graph that looks like this, the acceleration time graph is going to look very similar, just that negative means we're going to want to flip it. So where we start out with a positive maximum on the acceleration graph, we're going to start out with a negative, and then we're going to go up to it so that we get to equilibrium, no restoring force, no acceleration, amplitude, maximum acceleration, so on and so forth. So that is our way that we can get the acceleration graph from the distance time graph. Because in simple harmonic motion, we know that the acceleration is proportional to negative x. The acceleration is going to the graph is going to look very similar to the dt graph, just it's essentially flipped. So some key features, we could say that that velocity time graph and that acceleration time graph, they are shifted by 90 degrees. Like the curves will be a little different, but the shifting, like they have the same characteristic of that curve, they're just shifted. And then that dt graph and at graph, they're shifted by a factor of 180 degrees. So if your displacement time graph happens to be shaped like a cosine function, your velocity time graph is going to be the negative of a sine function, and your acceleration is going to be the negative of a cosine function. This piece here is more Math 30-1, so you'll have to wait until you get to that to explore this part a bit more in depth, but this is just to kind of introduce it to you right now. So we want to just finish out with this phase shifter. We want to talk about that. So when we talked about this displacement time graph, when the displacement was at a maximum of time equals 0, this gave us a cosine curve, or we could say like displacement was equal to cosine times t. So x is equal to cos times t. Now this doesn't have to be the case. We could certainly start something at a different position, but this is just what we've decided to start out with. Now, what we can do is we can vary these curves, but the main thing is we want to keep the amplitude and the period constant in order to say that the motion's simple harmonic, since we require that. Now, as we said, this red curve here, this kind of represents something starting at the maximum amplitude at time equals 0. But maybe we don't want to start at maximum amplitude. Like you see this blue curve. So instead of starting at instead of starting at 4 centimeters, we're starting at this isn't quite 3 centimeters, so this is about 2.8 centimeters. But then in this purple curve, instead we're starting at the equilibrium position. So these curves all have the same shape. They're just all shifted relative to one another. So they have that same basic, we'll call them sinusoidal shape, or they have that same periodic shape. We've just shifted them along the x-axis. So that amount that they are shifted relative to one another, this is what we refer to as the phase difference. And we can calculate that phase difference with an angle, how much they're shifted by, and this is what we call the phase shift. So the phase shift tells us how much one curve is shifted horizontally relative to another. So to calculate the phase shift, we will take the shift divided by the period, and we're going to multiply that by 360 degrees. So the phase shift is the horizontal shift on the graph. So let's have a look at this in a quick example here. So I have two curves. I have this blue curve, I have this red curve. I would like to find the phase shift between them. What we need to do is we need to find 2 points on the different curves that are kind of the identical points for both curves. So for example, I have this, I'm starting at this equilibrium position, and then I'm going down to this maximum here, or I'm going down to this minimum rather. Or I guess I should say I'm going down to this maximum below the time axis. So I could identify this point here. I want to find the equivalent point on the blue curve. So on the blue curve, I'm starting at this position, and I'm working my way down to here. So these are the same points on the curves, and they're on their respective positions on the curves, but they are shifted. If I moved this point to here, these two curves would overlap. We couldn't distinguish between the two. But what we'd like to do is we'd like to see how much is the red curve shifted relative to the blue curve, or vice versa. So the first thing is we need the shift. What is that distance? So this distance is going to represent the shift. Well, this point here, so at this, all of these tick marks here, they're going to represent pi over 4. So if I go back here, this is going to be negative 7 pi over 4. I should have chose some better points for this, but it is what it is. And then this point we have negative pi over 2. So let's find the shift. So the shift for this, we're going to have negative pi over 2, and then we're going to have this negative 7 pi over 4. So we got negative 2 pi over 4 plus 7 pi over 4. So this is going to give us 5 pi over 4. What that is telling us is to go from the red curve to the blue curve, we have to move this over 5 pi over 4 units to the right. That is the difference between these two curves. If you get negative here, like let's say you did negative 7 pi over 4 minus pi over 2, you'd get negative 5 pi over 4. that's fine. The phase shift can either be the plus or minus. Like it can be plus or minus that shift. It doesn't have to be specifically the positive or negative one, because it's all relative to one another. Now the period, we haven't really talked about the period yet, but the period is going to represent kind of that time it takes to make one complete cycle. So it doesn't matter which graph we pick, they're both the exact same period. So for this graph here, let's say I go to this point, and then to get a complete cycle I want to go fully down and then all the way up. So that distance here, that is going to represent my period. So that is the time it's going to take for this thing to do one complete cycle. So for this, my period, I'm starting at, this is going to be negative 3 pi over 4, and I'm ending all the way at what appears to be 3 pi over, no, that's, sorry, I got this wrong. This is 5 pi over 4. So I'm starting at negative 3 pi over 4. I'm working my way to 5 pi over 4. So the last thing I want to do is I want to calculate the period of this thing. So I have 5 pi over 4 minus 3 pi over 4. So then I'm going to get 8 pi over 4, or I'm going to get 2 pi. So what this is trying to tell me is that every 2 pi seconds, this pattern is going to repeat itself. So I know these curves are shifted relative to one another by a factor of 5 pi over 4. We know the period is 2 pi units. So the last thing, we're going to use this equation up here to calculate the shift. So the shift, or the phase difference, so we have that shift divided by the period times 360 degrees. So we're shifting by 5 pi over 4. We're going to divide that by 2 pi, and then we're going to multiply that by 360 degrees. So the pi's are going to go away. So we're going to have 5/4 divided by 2. We're going to multiply that by 360. So this is going to give us 225 degrees. So what this graph is trying to tell us is that these two graphs are similar. They're shifted by a phase of 225 degrees though. This is a really small point in IB, so don't worry too much about it. It's a really minor technical thing. We just want to bring it to your attention.